So this is question 2 from the 2020 MAT. The functions f of n and g of n are defined for positive integers n as follows. This question is about the set S of positive integers that can be achieved by applying in some order a combination of f's and g's to the number 1. For example, g of 1, so g of 1 is 4, then f of 4 is 9, g of 9 is 36, and then there's another example. So both of those numbers, any number that we can create, then goes into S. Fine. Part 1, write out the binary expansion of 100. Right, that's not what I was expecting. But, I suppose we have got multiples of, 2 and 4 and things like that. So this might work out in binary. So 100 then is 64 plus 32 leaving 4. So in binary, that's going to lead us with no 1s, no 2s, 1 4, no 8s, no 16s, 132, 164. So 1100100. Then we've got part 2. Show that 100 is in S by describing explicitly a combination of F's and G's that achieve 100. So how do we get to 100? Well, the only way we get to 100 is from G, isn't it? Because F's given us odd numbers, G's given us even numbers. So 100 has got to be G25. 25's got to come from F, so that'd be GF of 12. 12 has got to come from G, so that's GFG of 3, which is then the 3 has to come from F, so that's GFGF of 1, and we're back to the start. So that worked out okay. Part 3. Show that 200 is not in S. So 200, well, we've got the same starting setup then. It's G50. So that would have to be G again, but 50 is not divisible by 4. So 50 not achievable using G or F. Therefore, 200 not in S. Part 4, show that if n is in S, then there's only one combination of applying F's and G's in order to achieve n. So, for example, 67 can only be achieved by applying G, then F in that order. Yeah, well, this is pretty much what I've just been doing. Right, they're asking the same thing over and over here. So working backwards, there's only one route. Working backwards, we've got if the number is even, then it is from G. If number is odd, then it's from F. Therefore, only one chain from number back to 1. Right, so far so swift on this question. Part 5, let U subscript K be the number of elements n of S that lie in the range, n between, including 2 to the power k, but not including 2 to the power k plus 1. Show that relationship between UK plus 2 and UK plus 1 and UK. Right, we've got the binary coming back in then, because they put that in part 1. Nothing's happened here in the next 2 parts for binary. Now it's come back because we've got these powers of 2, which is what we're always interested in. So let's take a closer look then at F and G. What are they doing in terms of binary? We've got, right, so we've got the number times the base plus 1. So the way you want to, if you're not used to dealing with binary, I might be more familiar than a lot of you with binary. So I'm going to try and make this not look too obvious with dealing with it. But if you're dealing with binary, anytime you're multiplying by the base that you're working in, that's the same as adding a 0 to the end. So when we're working in decimal, in our base 10, if you multiply by 10, you add a 0 to the end. So it's the same thing here with binary. If you multiply by 2, you're adding a 0 to an end. Like if you've got 1, you multiply by 2 and you get a 1, 0. If you multiply by 4, you get a 1, 0, 0. So in this case with G, where we are multiplying by 4, we're adding 0, 0 to the end. It's the equivalent of multiplying by 100 in decimal because it's the base squared. Now for F, we're multiplying by the base and then we're adding 1. So we're putting the 0 on the end, but then we're replacing that 0 with a 1. So that's putting a 1 on the end for F. So that's how we're manipulating the numbers in binary. How that's got anything to do with what we're trying to show in part 5, I'm not entirely sure. So what would be going on in that? So we're trying to get things that are lying in a particular range. Okay, so this is saying any number which goes up to, so UK plus 1, UK plus 2. So we're saying the number of numbers, like say we'd started with, I don't know, some number, some range. So we got this range which is going up to up to 7. So say K was 2. So K is equal to 2. We want any number which is 111 or lower, but it has to be 3 digits. So if K is 2, we want a 3-digit number, or any 3-digit number. Yeah, anything in the 3-digit range. Okay. And then for UK plus 1, we want to have anything which is then in the 4-digit range. As long as it's got that 1 at the start and then 3 digits after it, then it will be fine. So how are we doing that then? We're pushing things, well, the only way we're going to get that is by pushing that up 1. So you push it up 1 and then we stick a 1 at the end, we're then in that range. So that would certainly work, wouldn't it? Because anything that you do, if you've got a number which is in UK, the number of elements of S that lie in that range. So, right, let's try and think this through. Any number counted in UK will be counted in UK plus 1 if it has F applied to it. Okay. And it will be counted in UK plus 2 and counted in UK plus 2 if G applied to it. Right, so that's nearly where we are, isn't it? So UK goes into UK plus 1 or it goes into UK plus 2. Right, well, this is counted in that. But that's not quite this equation, is it? Because that's saying that we've got... Oh, right, okay, yeah, I can see. I've just got a slightly different focus. So what I'm talking about here is how, if we're leaving UK plus 1, it either goes to be counted in UK plus 1 or it goes to be counted in UK plus 2. But here we're saying in order to be counted from UK plus 2, then it's either come from UK plus 1 or UK. Yeah, so to get into, right, let's go to a new sheet then and write that out again. Right, I've just got a sort of slightly backwards way I've approached it on that one. So to be counted in UK plus 2, the number was either counted in UK and G applied, because that's moving it up 2 buckets because we're adding 2 zeros to the end, or counted in UK plus 1 and F applied because we're adding a 1 to the end with F. So that means then, therefore, UK plus 2 is UK plus 1 plus UK. Right, okay, that was more difficult than the previous 4 parts put together. See what we got for part 6 then. So let S subscript K be the number of elements N of S that lie in the range, right, so the whole lot of it. So we're doing all of the previous ones then. Right, that is interesting. That is interesting. So how are we doing that then? How are we getting all of them? So if we're going to, say we're going from 1 to the next, if we're doing SK plus 2, SK plus, it's easier to think of it, right? So we're going from S, let's say we're doing SK to SK plus 1. So what is actually changing? We're doing, so SK, we've got all of those numbers in all of those UKs. And then to go to, yeah, so SK, that is then the sum from K, well, no, let's say N, usually I use K at the bottom of sums and N inside it. We're going the other way around here. So N is 0 up to K of UN. That's what we're saying SK is. We're summing up all of the UNs. So that means that SK plus 1 is SK plus UK plus 1. Yes. So let's write that out as well then. So we've got SK plus 1 equals SK plus UK plus 1. Right, that's good. Right, so I'm trying to show this thing. And where's that actually taking me on any of this? So we need an SK plus 2. So I probably would have been better off writing that as an SK plus 2, wouldn't I? Because we have to show that SK plus 2 is something. Let's go green. SK plus 2 is SK plus 1 plus UK plus 2. Oh, we know UK plus 2. We've just done that. So SK plus 1 plus UK plus 1 plus UK. Right, how has that helped? How has that helped? That helped at all? Not obviously so. We got an SK plus 1, right? I got the left hand side. I've got the first bit of the right hand side. Now I've got a UK plus 1 plus a UK. I mean, do we do it again? Do I do this thing again, but change it to K plus 1? I can't see anything else to do apart from do that. So I'll give it a go. I'm not convinced, but SK plus 1 plus, so UK plus 1 would be UK plus UK minus 1. And then we've still got that UK at the end. Right. I mean, I suppose we are reducing down these Ks. So I've gone from a K plus 2 to a K plus 1 to a K. So they are dropping down. We can do this K times. We can keep dropping it down each time as we go along. We got this one left over. We got a double here. So that is going to stay in place. We'd end up with an SK plus 1 plus a UK plus then split out the UK. So we'll have a UK. So if that was UK, that would then up be UK minus 1 plus UK minus 2 plus the old UK minus 1. So now we're going to have a UK minus 1 hanging around. Right, so I'm going to keep on doing this until that thing gets to U0. So we keep doing this until we get SK plus 1 plus, so we'll have a U0 at the end. We're going to have all of the, we'd have a U1, not K1, a U1 and a U2 and a U3 all the way up to UK. And we've got a duplicate. We've got this one, which is 1 up from the 0. So we've got an extra U1. Right. How is this helping? So we've got a sum of U. Oh, right. Okay. Yeah. All of this bit here is this sum. So that's sk. So I've got sk plus 1 plus sk, so sk is on the scene, plus a u1. u1 is the number of elements of S that lie in the range of u1. So this is k, so it's 2 up to 4. Well, 2 or 3. So how many 2s or 3s have we got? Well, we've got a 3. That's it. That's the only one we can get. So that is 1. Wow. Okay, that was as unpleasant as the previous part. So yeah, very strange question, that one. First 4 parts were pretty straightforward. The last 2 parts were pretty difficult. But yeah, well, I'd say the last 2 parts were very difficult. I mean, maybe there would have been some way of writing out. I suppose you could have gone through the permutations in part 5, actually do a branching diagram, but you've still got some way of actually having to show it, which is not easy to do, really, particularly if you're not that familiar with binary. I mean, I found this tough, and I've used binary a lot, and I still found this quite difficult. So yeah, I would say that was a tough question for at least the last 2 parts.